All right. Do the people online see the shared screen?
Yes, we can see.
Okay, thanks. Thanks for the feedback. So, good morning, everyone. Again, I'm Michele Claus, and I'm here with my colleague Valentina from Europe Research in Italy. It was really good that Ed already introduced many of the concepts that we'll now face with some hands-on training. First of all, again, we at Europe also worked from the beginning on the OpenEO project, and we really want to port it further and develop it further. We are trying to use it also internally for different research projects, because if you are not using it internally, then you really don't see the value. So let's start with an introduction of the concepts, even though some concepts have been covered already. Then we'll move to some practical examples using different OpenEO clients. And later on, if we'll have time, you'll also be able to try out your own algorithm if you have some ideas, and we could help you to try it out and implement it. So let's see if yes. So as Ed already mentioned, so why we actually started and why we need a common API, it was mainly, I mean, explained. So we would like to solve all the pre-processing part, the download of the data, the instancing of virtual machine, cloud computing resources, and all these things that our researchers would be nice that shouldn't care about, because if you spend so much time in creating your own VM, your own environment, then you don't have so much time anymore to do something meaningful. So that's why we would like to standardize the way that we access and process the EO data, and also share again the results in the most fair, compliant way. Again, this has been showed already. So the situation before was that every cloud provider had its own API, and thanks to the creation of this common OpenEO API, now we are able to perform the same processing, or at least calling the same processes in the same way on different cloud providers. So we do have multiple backends available around. We also have one at Europe Research. But the thing is that not all of them are operational, and not all of them are public. After the first iteration of the project, the Horizon 2020 project, we had multiple backends, but then the fact was they were mostly for research purposes and not available to the vast public, and therefore there was the OpenEO platform project that started. The idea was that we would like to really simplify how the actual user access OpenEO and use the cloud resources. And therefore, not only we wanted to have a single common API, which is OpenEO, but we also wanted to have a single account for each user. And that's why in OpenEO platform, we stressed a lot to have a single account, a single access point, which is now called openeo.cloud. So this is a single address where you can access different backends at the same time seamlessly. So you, as a user, do not care or do not know. I mean, you can know where the processing is running, but you just have one access point. And then depending on the data that you're requesting, depending on the processes that you're requesting, your process graph will be redirected either to the Vito Terrascope backend, to the UODC backend, or to the Sentinel Hub backend, which is really nice. It has also been demonstrated by Vito a couple of years ago. They've created an European crop type classification, which has been computed on multiple backends, so also demonstrating the capabilities of parallelizing the processing when creating large-scale workflows. Using again the same code, because it's the same language that you use, the same code, and then on the backend side, they're automatically sending requests to different entities depending on the load, and also, yeah, of course, if the data is available or not. So as I was saying, now with OpenEO.cloud, OpenEO platform, it supports OpenID Connect as the main entry point for the authentication part. And that's the most nice way. So you just have a single account. You can register using your either social or academic account, and therefore you don't have to remember multiple username and password. It's just a single one. And yeah, the next iteration, next evolution was finally the Copernicus data space ecosystem that also adopted OpenEO as an officially supported API, which was a really huge advertisement for OpenEO, for its API, because now it's really something which is operationally available for everyone. And again, both on the Copernicus data space ecosystem and OpenEO platform, you do have free accounts with a limited number of credits that you can use. A credit is basically unit of processing, so it consists of CPU processing hours and memory used, but that's something that is being computed on the backend side, and it's also available in the result metadata that you'll later see. So everything is traceable, so you can see what you run, what's the data that you have been using, so the input data, and also how much it actually costs. So as I was saying, we are putting a lot of effort in trying to make the results that we create with OpenEO as fair as possible. So looking at the various elements of the fair concept, it's findable because each job is provided, each job result is provided with a stack compliant metadata. Is there someone which is not aware what stack is? Maybe? Okay. So stack is basically standardized way to describe data collections with attached metadata. It's basically a JSON document. And this JSON document contains, for instance, the bounding boxes of the data, the bands, the description. You can also include a citation of a particular paper where this data was generated from. And but we'll have a look later on in details about this. So an example here on the bottom right, you see that this is a JSON document rendered, and you see that there's also included information about where this result was generated, which software version has been used. So all the information that would be important to have in order to reproduce the result. So it's also accessible because yeah, the files are provided with signed URLs. So whenever you generate a result, you get one or several links to one or several files that you generate, and they're accessible to everyone if you want to share them. For instance, it's also possible to share results in a nice way that I'll show you. Let me see if it opens it. It's here. So basically, with a signed URL and a link to a public file, you can also share a custom map which is showing the result. Here, for instance, this a project that we have worked on recently. It's photovoltaic panel mapping, which has been implemented in OpenEO. Yeah, basically you can generate your result, you can share it easily, and yeah, you can also have a look with different base layers. It's kind of yeah, WebGIS where you can interact with the data and yeah, have a look at your results. If you have any questions, just stop me and we can discuss. No issues. Yes. Just come here in case.
Okay, now it's working.
Yes.
For the stack catalogs, so basically do we require a special stack catalog for OpenEO and another stack catalog for another, let's say, platform or environment?
What do you mean?
Because is it only one? When we have a data to expose to the OpenEO platform. So
no, I was mentioning about the results, so not the input data, but the output currently. So if you generate, you have your OpenEO process graph, you generate the result, then you have the result as a stack collection that you can also reshare. Instead, the input data could also be a stack collection again, but it has to be publicly accessible. But later on, I'll show you the difference between the actual OpenEO collections and stack collections that are available to the public. Yeah, then covering the interoperable part, yeah, the file formats used for the results are commonly used in the geospatial domain. So they are GeoTIFFs, NetCDFs, ZAR, JSON, GeoJSON. Recently, we've also added the support to GeoParquet for the vector data, and they are directly reusable also with third-party tools like QGIS. Again, for the reproducibility, we do include all the metadata in the stack metadata. So there's the OpenEO process graph, the software which is being used, and it would be also possible to basically create a little container of your workflow directly as a user-defined process to make it. Paolo, could you mute yourself, please? Thanks. Yeah, creating a user-defined process would create like a little new process that contains multiple other processes and that can be reshared and reused even more easily. As Edward was mentioning, we are building a community behind. I mean, there's a community, but we are trying to enlarge it and really support all the new users coming to the OpenEO world. There's a GitHub repository which is maintained because we do have several repositories with multiple examples from previous projects and previous results. But as you might know, it's not that easy to maintain multiple Jupyter notebooks with multiple versions of software running. So now we really decided to focus on a single entry point repository, which is the OpenEO community examples, where we could share Python, R, JavaScript, and other examples, which are also maintained, which is not obvious. Again, yeah, maybe it wasn't that clear, but OpenEO can be accessed through several different programming languages. In the tutorial, we'll focus mostly on the graphical user interface and the Python client. If there are some R specific users, you could also try. There's the documentation. I'm not personally an R expert, but there might be some here in the room. So we could also try to reproduce the same workflow in case. Again, for the support, there are actually two different places to go apart from the GitHub repositories. But I would say that since on GitHub there's quite many repositories under the OpenEO project, it might be difficult for you to find the correct one where to open an issue. So depending on which actual OpenEO backend you're using, you should go to either the OpenEO platform forum or the Copernicus Data Space one. Both are publicly accessible. You have to register first and then you can post new questions. Maybe something that hasn't been addressed previously about the standardization part. So recently, OpenEO has been also, I mean, it's still in the process as becoming an OGC community standard, but it's towards the end, the voting session and the approval, which is also a really nice achievement of OpenEO to be recognized as, a standard that should be used quite frequently. And not only OpenEO, but also the Stack catalogs. The Stack API has been going through the same process, so it will also become an OGC community standard soon. As Edgar mentioned, we at UX Research recently released an online course, which is called Cubes and Clouds. It's available on the EO College website, and it really tries to cover many topics of the open science world, from the basics, from what's a license, which one you should choose to share your data, to where to actually find the data, what are the different cloud platforms available, what are the different languages that you can use to do EO processing in the cloud. We also created several interactive videos to explain the concepts directly, so not just with text. So it's composed by theoretical lectures, interactive exercises, and hands-on trainings using Jupyter notebooks and the OpenEO Python client. So if you are interested later on to go deeper in this topic, please register. The course is for free, so you don't have to pay anything, and there's no limitation in terms of time that you should be spending on it. And at the end, you'll also get a nice certificate with all the topics that have been covered that you could also reshare on LinkedIn to your colleagues, and which in theory should prove what you have learned during the course. So how does it work? OpenEO in general, Ed already mentioned that in OpenEO you create a workflow, a process graph, which is then translated into a JSON document, like here on the right, which is programming language agnostic. So you can create it with the OpenEO Python client, the R client, the QGIS plugin, the JavaScript client, but all of them will create the same structure, the same document, which then will be sent to the OpenEO backend. Here there's a little video of an example of the graphical interface of OpenEO, which is called the OpenEO web editor, which later we'll also use together. We could look for the required processes, drag and drop it here. In this case, it was the photovoltaic mapping process that I've created. It's a user-defined process which combines multiple ones below, but here you don't see all the others because they're basically hidden, and it's quite handy for resharing complex workflows where you just select, for instance, the area of interest, the temporal extent, and then you just start it, and then you can reproduce the result which has been developed. And you can also visualize the results interactively once they are ready. Okay, I prepared a list of frequently asked questions, but I would like to move to the practical part. So firstly, are there questions to the concepts that I've explained now? No. Did you manage to create an account on the Copernicus data space? If not, would you try to do it now? Is there someone that didn't? do that yet. Well, if you are all ready, I'll proceed and not wait. Let me know.
Yeah, but I think making a count there, it's not a big, shouldn't be a big issue. Yes, it's just a few minutes.
Yeah,
So
exactly.
Yeah, if
So
somebody still doesn't have it.
If you have to register, just go to, well, look for Copernicus data space. You'll basically see this web page here. And then if you click login, well, now I'm already logged in, but basically you'll see either the login part or the register on the right. And yeah, you should be able to register quite easily. It just takes some seconds.
It's actually quite cool because this is like a brand new European platform. It should have a lot of data around, so we can test it. Yeah, within OpenEO.
And the Copernicus data space offers various different APIs to get access to the data. And among them, there's the OpenEO API here. So basically, if you go under Analyze Data and you click on OpenEO, and then here, if you click on OpenEO again, it will open up the graphical interface of OpenEO, the OpenEO web editor. This is the main view of the OpenEO web editor, where you can inspect what's available on the backend. On the left-hand side, on this panel, you can navigate through the data collections. For instance, you have all those data collections here. It's also interesting because you can also get a preview of the data, clicking for some of the collections. If there's this little map logo, if you click on that, it will open up a preview panel. For instance, for the ESA world cover, and you'll be able to navigate through the data. Mostly for, I guess it's easier to do this for collections that do not have the temporal dimension. It's also possible to do that for Sentinel-2 and Sentinel-1, but probably it's going to show the last available acquisition. Yeah. So here on the left panel, again, you see the collections that are available on the backend. You also see the processes, because in OpenEO, we do not only define the way that we interact with the backend, but also the actual processing part. For each process is being defined as a JSON document. And for instance, if you click on it, you'll get all the information about that particular process. This one is called, for instance, aggregate spatial. It's used for computing statistics using raster and vector data as input. So using the vector data as boundaries for computing the statistics. And you'll see how the parameters are defined, the input data, the geometries, the reducer, which is the operation that you actually want to be performed on the selected data, and so on. So in OpenEO, most of the things are defined as JSON documents, but then they are rendered differently or similarly in the various clients. So you shouldn't be scared to these kind of things that are text-based representation. So you might see that on the bottom side, there's still the login button, and here there's still written that we are a guest. That's because those information are available to the public, but as soon as you want to actually do some processing on the OpenEO backend, you have to authenticate. So if you press login, then you have to press login with Copernicus Data Space Ecosystem. And now on the bottom part, you'll see appearing a new area, which is showing your batch jobs, previously run batch jobs. Probably you won't have any if your account was recently created. So in OpenEO, there are two ways of running processes. One is the synchronous call, which is basically sending the process graph to the backend and waiting for the result to come, which is ideal for quick prototyping. So if you are doing something new and you want to test it on a small area, this is quite nice because on the backend side, they are running it immediately. But you have to be aware that this is suitable for just requests that are taking, I guess, less than 2 minutes. Otherwise, they will be stopped, and you'll have to use the asynchronous calls, which is the batch jobs. So you basically create your process graph, you send it to the backend, and then wait for the process to finish, and then get the results later on, even days or weeks afterwards. And here in the bottom part, you still have the list of processes that you have run, batch jobs that you have run previously, and you'll still be able to see what you did 1 week ago, a month ago, and so on. Here there are several buttons. So the first one will show you the details of the job. So for instance, the batch job ID. So every batch job that you send to the backend is being assigned with a unique ID. So this ID will identify your job and will be useful to retrieve again information about the job. If you have problems and you go to the forum, you might post directly to this ID so that the backend developers can also inspect what happened if something went wrong. It also includes the costs of this processing. For instance, in this case, we use 2 credits, and also more information about the CPU seconds that has been used, the number of pixels that has been used, memory, and so on. It also includes the process graph and the results. This is basically the JSON stack document being rendered in a graphical manner. But at the end, this is just a text file that could be reshared to someone else and reused. So now, yes, Leandro?
If I have, for example, some existing map that I want to upload, some custom map to integrate in an OpenEO process, is it possible?
It is possible if, I mean, you can't upload it directly to the backend, but you could create a stack collection and then use it as an additional input data. In fact, my colleague Valentina is doing the same for some Modis data, which is not available on the backend. We did create our own stack collection, which is publicly available, and then you can use it here on OpenEO.
Is it possible to create a binding with the local file system? So it will be useful for, like, I don't have to change my file system. I don't have to upload stuff, but I can run through.
It is possible to use OpenEO locally on your own files. And later I'll show you how to do that. But it's not possible to mix processing locally and in the cloud. So again, if you have some local files that you would like to use in the cloud, so either you create a stack collection, or Vito does offer a kind of data storage for user storage, where you could upload some files and reuse them, but it's not a standardized way to do that.
But Michele, this stack collection, does it has to fulfill some standards or for OpenEO, or it's just any stack collection?
Yes, exactly. We are working on defining the, let's say, best practices to do that. Yeah, I think that there should be some documentation later on, I'll check. But yeah, ideally it should include some extensions like the projection extension, the raster extension that give additional information about the data projection, the resolution, the actual bands that are in the collection. Yeah.
So it's basically, so you will be working on like a minimal metadata requirements
Yes.
for stack. So, but of course you can handle much more than that. Yeah.
Yes. And then it really depends on the actual implementation of the backend, because there are different implementations of OpenEO. For instance, the one running on CDSC is the one of Vito, which is written in Scala, Spark, and Python. Instead, there's another major one, which is we use at URAC. It is being used at UDC, and it will be also used by IBM and DLR, and it's based fully on Python. And therefore, it really depends how this process, which is called load stack, is actually implemented and which are the requirements. But we are working on, let's say, agreeing on a minimum level of metadata.
But and what happens in the background? So with the data that are locally stored and then exposed, like let's say cloud optimized geotiffs or whatever.
Well, you should share them in some publicly available heap or URL or.
Okay,
bucket.
and then it's like so everything is processed on another backend, or like okay, here CDSE,
Yeah.
but yeah, the credits are taken just. But are the data then stored locally? Are spent some credits for storing the data or not?
That's something that you should ask directly to Vito, for instance, because we do use it quite frequently now, but we don't have access to the details. So that's something interesting that we should clarify. Yeah.
It's not clear to me. So by providing a stack collection, you mean you have to load your data on Vito, I mean, and then expose the metadata via stack, or you have to provide your own service with all.
You should provide your own JSON document with the metadata and the links to the files.
So
But
eventually on a public cloud, a generic public cloud,
Yeah.
in a static way, without a RESTful service, I mean.
It depends, because if you want to load just a single item, it's fine to have a static file, which is self-describing. So a single, let's say, a file or a position.
Okay, so with a sort of XML description for.
But later I'll show you some examples.
okay.
So maybe we can go on. So did everyone manage to open the web editor and log in? Okay. There's a nice tool for new users, which is called Wizard, and you click on it, you press OK. It's basically allowing you to create an OpenEO process graph interactively in an easy manner. So for instance, it will ask you what you want to do. Should we just try to download some data or compute spectral indices, for instance? Other examples could be added in the future depending on requests. So we could try to compute our spectral index today. Now it will load a list of data collections that are available. For instance, we can use Sentinel-2, level 2A. We click on it. Then we might choose among several different spectral indices. Let's not use the usual NDSI, but something different like the NDBI, so the normalized different built-up index, which should show us differences between urban and not urban areas. Then you can select the area of interest. Let's try to come here to Luxembourg. So everything that we are doing here in with this tool graphically can be also done programmatically via Python or R or JavaScript. Wait, where's Luxembourg here? Okay, we might select an area which covers urban and not urban, just to see if we see the difference between them computing the NDBI. Then we select next. We do select the temporal extent. Let's go to some recent years like 2023. July 1st to the end of July. I'm trying to use the summer months because here we are not masking out the clouds. And then it's asking, do you want to create a temple composite? So if we say no, we'll basically get a result which consists in the normalized difference built-up index for each acquisition time. But in this case, we just want a single result. So we do want to compute the average, for instance. So we select it and we press next. And finally, we want to we can decide which is the file format that we use. In this case, we select GeoTIFF. And additionally, it's also asking, do you want to scale the data which is being computed and original between -1 and 1 to 0 and 255 for visualization reason? Yeah, let's try to do that. So we click on this and then press next. Finally, as I was saying, it's possible to run the process in different ways, either as a synchronous processing, so it's fast and it's meaningful for small requests, like in this case, but we want to try out the batch jobs so that we can also look at the metadata later. Select batch jobs and then press create. And then you'll see appearing the OpenEO process graph in the top part. And the job here in the bottom part. Here you see that the job has been created. And if you press start processing here or on the play button here, the job status will change from created to queued, because the backend will decide when the job will be started. So it's not obvious that your job is being sent and then immediately running, because it depends on the backend load. So now the job has been successfully queued. Then later on, the status will change again to running. And when the job will be finished, it will be changed to finished. Here on the top part, you see the graphical representation of all the steps that we have created. Usually an OpenEO process graph always starts with loading the data, and the process is called load collection. And this load collection process consists in the name of the data collection that you have selected, which is Sentinel-True Level 2A, the parameters, so the spatial extent that we also interactively select, the temporal extent, the bands. The bands in this case has been automatically selected to compute that particular spectral index. And you could still modify the parameters and change it if you would like to. I know I've opened it multiple times. Then the second step is a reduce dimension step. It means, so you have several dimensions. You might have spatial dimensions like lat long or XY. Then you might have spectral dimensions such as bands for Sentinel-True, and the temporal dimension. In this case, since we want to just get a single result out of a time series of data, we want to squeeze the temporal dimension to a single value. And therefore, we use this process, which is called reduce dimension, and we compute the average over time. Again, also for the index, so for the NDBI computation, it's again a reduced dimension because we reduce the bands dimension, which is composed by multiple bands, into a single value, which is the index value. And finally, there's another process called apply. The apply process applies a function to all the pixels. And in this case, this function is, you can inspect here, and it's a linear scale range function, which basically translates the range of values that the data has from -1 to 1 to 0 and 255. And finally, the save result. So ideally, the OpenEO process graph always starts with loading the data and finishes with saving the data. Now the process is still running, but I have one here that have been computed previously. And the various button here, the meaning is, so getting the information, we already did that. Reload the process graph. So if you click on it, you basically reload the process graph. By the way, here you have the visual representation, but if you click on code, you'll also see the JSON-based representation of the process graph, which you could copy and paste, and you would get the same workflow appearing. Then you could delete your job. You could download your results. So if you press download, you'll see appearing the metadata of the result, and you could download the result here, copy the URL to the file, or visualize the result, which is here. Let's see if we somehow binarize the data. So this is basically the normalized build-up index computed in a super quick manner, and yeah, somehow it resembles the urban area. I wanted to show you another nice thing. So if you have your result and you copy the URL, you could open up QGIS. If you have it, if you don't, just look at the example. In the meantime, someone of you did manage to start the processing. Did someone of you? No? No, okay, but you were able to create the job? Okay. So now I've opened up my QGIS, and if I do add layer, add raster layer, and I provide the URL to the result, I can directly stream the result to my QGIS instance without downloading it directly. And I could also, let's say, use it for other analysis combined to other local data that I have. Additionally, as I was saying, all the results are provided with stack compliant metadata. There's another button here, which is export share. If you press it, once that you have the result computed, you'll be able to copy the address to the stack metadata. And then if you open up the stack browser, which, by the way, now I'll explain you what it is. So if you look for stack browser online, you'll find the Radiant Earth web page hosting the stack browser. The stack browser is a graphical interface to explore stack catalogs and collections. And here it's also listing publicly available stack APIs catalogs. But the nice thing is that if you paste here your stack compliant document, and if you press load, you'll be able to see all the metadata of our job. So we do have the geotiff here, the result on the right-hand side. We have the provider with the OpenEO process graph included. And we also do have all the original Sentinel-2 files listed that are being used for generating this result, which, in my opinion, it's the most complete way to document what you have been doing. And yeah, this includes a lot of information to replicate what you have done in this really, really simple use case. I can close this. Where I am here. Okay. My job has finished.
Just a question. How many
Yes.
credits are available per person?
As far as I remember from the Copernicus data space, maybe 10,000. I'm not sure, you should check on their website. For OpenEO platform, I guess more or less the same. But yeah, you should check directly on their website. And for instance, this simple process took, let's see, how many credits, but probably 1 or 2, just a little amount. You have to remember that the credits are composed to the actual processing time, but also to the number of input pixels that you're using. So if your process graph uses a full Sentinel-2 time series, this will for sure use many more credits, even if the area is small, because it has to take into account millions of pixels. So for instance, this little job just took two credits.
Thank you.
Michele, if we want to like export maybe code to GitHub or reposit the outputs to Zenodo, are there any links already? Or to like deposit all the code to maybe Docker Hub? Are there any links to automate that, or you have to do it manually?
No, you have to do it manually now. There's no automatic way to do that currently.
But if you could combine GitHub, Docker Hub, and Zenodo, then you could have the whole workflow.
Yeah, that's true. Once we are currently working on a easily deployable OpenEO backend. The only issue is that, I mean, you can have the whole API and the processing part Dockerized, but you do also have to provide the data. So either the data is also again provided by a publicly available stack collection, but then you depend on that. So there, or you also provide the input data if you want to make it fully reproducible. So somewhere you depend on someone.
And if you want to make a WebGS from this map, it's possible?
It is possible in the not with the Copernicus data space, but with OpenEO platform. Opening up now you don't have the account, so you can't do that now. But with the OpenEO platform account, it's possible to create. It's called, let me see, let me log in first.
Sorry, in the meanwhile, I just wanted to add to the question of the credits that anyway, every month they get renovated. So if you plan the use, it's not a problem. And again, as Patrick mentioned yesterday, whenever you have a running research project, you can still ask for this NOR sponsoring from ESA, which will support you both in terms of credits, but also in terms of developer support. For instance, I did request this for this photovoltaic mapping project that we did recently, and it was really nice because you do have a direct connection with the OpenEO developers. For instance, those were the ones from Vito, and therefore it's much faster to port an algorithm and develop it. So Tom, for your question, it would be possible to create, now I don't have an example running, but it would be possible to create an OpenEO process graph and then register it as a web service here. And then it will be similar to Google Earth Engine, where you can basically navigate through the map and your result will be computed on the fly.
Examples? You don't
no, here, no, I'm sorry. But the limitation is that it runs only on the Sentinel Hub backend because they're providing this functionality. So only the data collection that are in Sentinel Hub, which are stored with the pyramids and they can do this kind of processing on the fly, are allowed to create these WebGIS or web services. Okay, then let's try another little example from scratch. If you press here, new script, clear current script, it will clean up your workspace. And then let's try to do it manually without the wizard. So again, let's start with sending it through L2A. We have the collection on the left side. If we click and drag and drop to the workspace, it will appear here. And in the same time, you'll see that in the code, this is being translated in a load collection step. Then let's set the parameters. Here, top right corner, click, and you can change the parameters. Let's again go instead. Let's go to Bolzano, where UX research is based. I mean, you can go wherever you want in the world. Let's select a small temporal extent. In this case, let's try to do, I wanted to do something recent, but it has been raining all May and June recently, so probably it would be too cloudy to use the recent data. So I'll use again July 2023 and to the end of the month. Now I would like to, no, it didn't work. Okay, I would like to create an RGB composite. So I have to select the bands that I want to use. I will use the blue, green, and red bands, so which correspond to band 2, 3, and 4 in Sentinel-2, and then I click Submit. And this just generated an updated JSON representation of what I want to do with the updated temporal extent and bands and so on. Then again, I want to compute a single value out of this time series of data. I look for the reduced dimension process, drag and drop here, connect. So to connect the input to the process, you click on this box and then drag to the input of the next process. And then I want to compute the median over time. Again, drag and drop data. And then set the dimension to T for temporal. And finally, I just want to save the results. So I look for the save result process, or here there's also a list of export file formats. If you drag and drop GeoTIFF directly here, it will be show up directly with the specific format. Now I have my super simple OpenEO process graph, and I can click Run Now to ask for the backend to process it immediately. And soon we'll see the result appearing. So previously we used the asynchronous calls. So we start the job and we have it listed here, so we can reuse it later on. In this case, we just want to prototype and see what's happening. Now I get the file, I can download it, but it's also showing up here. I can select which band correspond to red, which band correspond to blue, and then set some minimum values and maximum values. It's complaining that there's no maximum value. And now we see our Sentinel-2 RGB composite and UREC researches here. Another really cool feature of the web editor, when you want to transition from this, let's say, naive way to interact with OpenEO to a more programmatic way, there's a button here, which is this one. It's called, the function is export into another programming language. And if you click on it, you'll basically get the translated process graph to either JavaScript, Python, or R code, which you can directly use to start prototyping in the different programming languages. I have to be honest, it's not perfect yet, but it's a good starting point. So you might still have to add a couple of steps, for instance, the authentication, but there might be some comments that you can follow. Other questions until now? Were you able to generate something? Hands on if you were able to generate something. One. Only one. What's the status of the others? It's running. Yeah, probably since you all started together, they are all in the same queue. Yeah. Yes. Does the microphone work or not? So I just repeat the question for the online audience. So if it's possible or recommendable to download data, it's doable. I mean, you can definitely use OpenEO to download the data, but the idea is that you should try to do as much processing close to the data in the cloud as possible. But of course, if you want to do something and you just need to get the data which is available via OpenEO, yeah, you can do that. You can still just use OpenEO to get your area of interest, yeah, slice the data and then just get it.
It is possible to check the number of credit that has been used in this fast process.
Good question. I think so. There should be. Let's go to our Copernicus web page. If I go to my account, opening up the account information in under maybe personal info. No, dashboard maybe. There's a dashboard that shows the credits that are being used for each job or call, which I'm pretty sure it's available for OpenEO platform. Now for CDSC, I haven't tried yet, but probably there is. Let me try to look for it. So monitor your usage. Dashboard. Okay, here. No, but the question is if you can see how many credits you use for the synchronous call, so which is not generating any job. So here on the dashboard, we do see the credits, and I guess that yes, okay. So the amount of credits they have is 30,000 consumed since the 1st of January remaining. Last hour, if I press details, yes, here. So here you see the requests. No. Probably there's a way, but I haven't tried yet.
Maybe
Sorry.
it still has to update.
Yeah,
Since
probably so. Because
it said that you didn't use.
I'm aware that until some time ago, I guess that the synchronous calls were not even, let's say, counted. So they were basically for free. And now they started to also measure the resources that are being used for the synchronous calls.
Thanks.
Dashboard. Should like a manual reduce damage. Yes. So firstly, I looked for the reduce dimension process. I dragged and drop into the workspace. Connected. Then top right corner, there's the button to change the parameters. And under reducer, again, there's a panel where you can look for the processes. And you could look for median and port it here. Another nice thing here is that you could write your own formula, mathematical formula, and this would be translated into a process graph. For instance, for if we want to compute an NDVI or like an index, we could refer to the bands like B0, 8, B0, 4. Well, let's see like this. And this will be directly translated into a process graph. If I press insert, you see the corresponding elements appeared. So array element means I select a single element in the array, for instance, the band number 4, and I select also the band number 8, and I perform the subtraction. And it's exactly what I've written here, which is also handy. But at the end, if you do this kind of more complex stuff, you do it directly in Python and not here.
I can also upload my Python script and using this.
No, no, you can use your Python client to create a job and then visualize the results here. Later, okay. we'll do that together. Yeah. So those are basically, yes.
Just a question, but for the visual thing, is it possible to have a look to example for scripts within the tutorial, maybe in the tutorial of the service, just to have the possibility just to write down some example script without using visual stuff, which could be quite complex for choosing parameters and so on, maybe.
You mean anything to have examples on
sort of
visualizing data?
Yeah, just something such as a sort of the source repository for common.
Yeah, we do have the community example repository, which now we'll look at together.
Okay.
But using the Python client.
Thanks.
So if you don't have any more questions for the web editor, we might have like 5 minutes of break. And then we can proceed with the Python part. You agree? Okay. Someone asked me about a particular data collection, so just wanted to make you aware that maybe some collections are still somehow experimental. So basically, when you decide the data collection that you would like to work on, there's, for instance, this Copernicus vegetation indexes collection, which states here it's experimental. So it might be possible that if you try to use it, it doesn't work properly. Then also look at the temporal extent. Yeah, because sometimes you might, your process might fail. There's also the debug button in case. So there's this little bug icon. And if you press view logs, you can see the logs appearing. And if some error occurs, you could also filter through the different warnings, levels, and error. In this case, there are no error messages. But if something doesn't work, you might see some informative messages here. So whenever you're ready, we can start the Python part. For the Python part, we'll use the hosted Jupyter Hub environment from the CDSC again. So you don't have to install yourself anything. You can just use what's already available. and you can start the Jupyter Lab under the main Copernicus Dataspace Ecosystem webpage. You press Analyze Data, you press Jupyter Lab, and then access Jupyter Lab here. And this will allow you to start a Jupyter Lab instance. I guess that in this case, it will be appearing already for me because it's already started. If it's a first time for you, you will be asked to choose among 3 different sizes of the actual server that it will be starting. Please try to use, I mean, there will be a small, medium, and large server. Since I will also try a couple of examples that are doing some local processing, please select the large one, so we do have some more memory to play around. Otherwise, even the small one would be fine to interact with the cloud environment of OpenEO, but then later on, if we want to process the data locally, we would need some memory allocated. So please go to the Copernicus Dataspace Ecosystem webpage, Analyze Data, Jupyter Lab, and then request for a large workspace or server. And let me know once you're ready.
Michele?
Yes.
What is really the advantage of Copernicus data space ecosystem? So is it so the data that are already in OpenEO offered by other backends, they are still there, but is there some extra data or?
Yeah, okay. No, the Copernicus data space ecosystem is it's a service offered directly by Copernicus with Copernicus data. So it's not the same data which is in OpenEO platform, because OpenEO platform aggregates data coming from Vito, UDC, and Sentinel Hub. So in practice, there are more data collections, and instead here in the Copernicus data space, you have the ones. I mean, slowly they're adding new ones, but you mainly have the Sentinel missions and maybe some other ones. But for more particular collections that might be available only on OpenEO platform. And the advantage is that is officially supported by Copernicus. The advantage of using OpenEO is that you process the data where the data is, so you don't have to transfer it around. That's the main advantage. Yeah.
Is there, for example, some products like Gamma Knot or so, like Radar Sentinel-1, or it just GRD like or
yeah
level 1 data?
Let me see. So there's for sure the GRD collection, and there's a process to compute the backscatter on the fly. Not sure if there's a pre-computed gamma node collection in CDSC, but there's one in OpenEO platform. But it's also possible to compute it quickly. And the nice thing is that once that you, let's say, select your area of interest, you compute your backscatter, and then you can reuse it. Because once that you generated your result, which is available as a stack collection, then you can reload it several times. So the nice thing is that you can do your pre-processing once and then reuse it several times for prototyping and changing the algorithm parameters, and you're not incurring in several times the same cost because the pre-processing time has been done once, and then you can just reuse the results.
And so I know that there is available Sentinel-1 data for Africa. So I think this is already in OpenEO, Gamma Knot.
I know that there should be the global connection. Let me see.
Yeah. But I remember there was one ESA project for South America when they process Sentinel-1 data. Do they integrated this to OpenEO platform or not?
I don't know. No, I'm not aware of it.
Yeah.
I know that EODC hosts.
Yeah, because that's really a pity because this was a big ESA project, and yeah.
But didn't you use Sentinel-1 during your use case for OpenEO platform when mapping the deforestation?
Yes, yeah, but this was provided by this was Sigma Not and provided by UDC.
Let's see if there's Gamma.
Yeah, but there are other initiatives.
There's Sentinel-1 Gamma node from Terrascope apparently, but it says deprecated. Use Sentinel-1 GRT Sigma node. Strange that it mentions Sigma node and Gamma.
Yes. Yeah.
Let's see what's inside here. Maybe there are different bands. No. But basically, yeah, I guess that the way would be to use this backscatter process and then basically computing the should be possible to compute Gamma node on the fly. Apparently, there's no pre-computed collection.
Yeah, but it's, I mean, computing again, it will cost a lot of credit. And for a large area. That's really a big, it's really a big problem. In fact, because there are so many projects funded by European Commission or ESA, and especially for processing big data on different parts of the world and even continents. And at the end, they don't end up in those repositories.
In fact, even us at EURAC, we are also needing that data, and we ended up using Microsoft Planetary Computer with their stack catalog, and we are basically pulling the data from there and using it on OpenEO.
I forgot. I should have asked Patrick yesterday for Yeah, but there is a Living Planet Symposium soon.
Yeah, exactly. So did everyone had access to the Jupyter Lab instance? Yes, large workspace. Yeah. Okay. So now I'll ask you, since you won't have any, let's say, file available, to clone one repository. So it will be the community examples repository. I will send the link maybe in Discord. It's community examples. OpenEO community examples is the repository available under GitHub. So basically, you can just press Discord now. Code. So git clone this repository. I'll do it as well. So this is the main view of Jupyter Lab. You see here that you could do several things: create a new notebook, start a Python interactive Python console, or even R console, but it's not RStudio. And you can also open a terminal, for instance. Please click on terminal. And now you can clone the repository where we have the examples. I'm not gonna clone it because I have it here already. Once that the repository is cloned, you'll see the folder appearing on the left side where there's the file explorer. And then if you navigate to Python, and the first one you should see is the Getting Started guide. Click on it and open the Getting Started notebook. Let me know whenever you have the notebook open so that we can start trying it out. Yes? I don't know, but you can still try out these examples. Later on, when we'll try the local processing, it might not work. So you could try to switch server. Anyway, in case you have your own Jupyter instance running, you could also use that. So you're not forced to use this one, but it's just for simplicity because there's already a predefined kernel available. In fact, if you go here, top right part, you can select the specific kernel. There are several ones. Select the OpenEO one. There still might be some libraries, modules that are missing, so we could still install them in case. So here it's mentioning how to install OpenEO. It's easily installable via pip or conda. And you can just import OpenEO like this. To run a cell here, you can either do Control Enter or clicking the play button. So the first step, as we did before, is to connect to a specific backend, which is in this case, again, the OpenEO dataspace from Copernicus, and authenticate. Again, we run the cell. Here I was already authenticated, so it uses the cache token, but in case you're not, it will show an address. You have to click on this address, log in with your credentials, and then you should see here like authentication successful. Let me know if you manage to do that. I've sent it in Discord, but you can look for OpenEO community examples.
Michele, there is a question from on Discord. Is there is a tutorial they can follow? They have issues with the internet connection, or just they can start now with this. Yeah.
Yeah, this would be a good starting point. This notebook.
Okay.
Maybe for the ones online that have connection problems in Teams, you can deactivate the videos, the input videos. So maybe you can spare some bandwidth. So you'll just see the shared screen and not my camera and the audience camera. So once that you are being able to connect and authenticate, you can start discovering the data collections. So the main object that we'll work on is this connection Python object, which includes the details on how we connect it to the backend, and we can start from there. So first operation, list the collections IDs. And instead of showing them as a list, it's also possible. So in Jupyter, if you press plus, it will create a new cell, which you can interact with. If you do, instead of list collection IDs, list collections, it will show the graphical representation of all the collections with the same metadata that we have seen on the web editor. So here you click on a collection, you get description, temporal extent, spatial extent, and so on, land cover. You get also various links for the information from the product viewer if you want to interact with the data, and so on. Then we close this. And then we can also get the specific metadata of a single collection. If we want to interact with the Sentinel True Level 3 collection, we do describe collection, the name of the collection we are interested in, and we have everything here, preview, spatial extent, and so on. The bands with the corresponding wavelengths, the data type, and so on. Okay, so this is all metadata information that are publicly available. You can do the same thing for the processes. So basically the list of processes that we were seeing previously on the web editor, we also have it here. For instance, previously we were looking for the reduced dimension process. It's here with the metadata. This is just to explore what's available on the backend. Again, you can get the description of a particular process. And again, this is the discovery part. Now we actually want to do some processing. And again, as we did before on the web editor, we start with the load collection step. Now you see here you don't have to manually select area of interest, bands, and so on. You just write it down. So you select, you write down what's your collection that you're interested in, bounding box, temporal extent, and bands. Let's execute it. And now the nice thing is that if you then inspect this object that we created, it will be also rendered in the same way which is rendered in the web editor. And you can also get a visual representation of your process graph in the same way that you have on the editor, so that you can, because sometimes when you work with complex process graphs, you might lose the track of what you're doing maybe, because in Python, if you overwrite a variable, it might chain the operations multiple times. So this is also a possibility to inspect what you're doing. Now, in this case, there's a single processor. It's not so meaningful, but later you'll see that it might be more useful. Anyway, you can also read through all the information that are being provided, but we have covered mostly of this information previously. Now there's again an index computation, the enhanced vegetation index, the EVI. And now in this case, we don't have to do all these drag and drops for computing such an index, but we can just refer to the band directly. And at the end, the actual formula expression is identical to what you would do with NumPy, for instance. So you create blue, red, and near infrared objects containing the bands. And then you just do EVI equal the formula referring to the bands. And then you have it. And again, if we inspect the content of this EVI cube, we'll see that this call here is being translated into a reduced dimension call. And inside of the reduced dimension, there's this AVI computation, which takes the various bands as input. They multiply it by the scale factor for the Sentinel-2 data to transform the data from digital number to reflectance values. And then you have all the arithmetic to get the final EVI value. So again, this looks like an actual calculation, but there was no processing going on. Now we're just creating our workflow, but just when we'll send this process graph to the backend, the processing will be triggered. So now we are just interacting with metadata. Again, now we are working with a time series of data. We would like to get a single value. We can call the max time function, which is a wrapper to say, do the reduced dimension over time and take the maximum value. In fact, again, if we inspect the produced process graph, we see that it attacks another reduced dimension process over the dimension t with the maximum reducer. And finally, we can trigger the processing on the backend, and we can do it synchronously, so it will be pretty fast. And the syntax to do that, in this case, is .download. You provide the path to the file that you want to create. In this case, the client automatically understands the file format that you want to generate. So if you do EVI composite.nc, it will download an HDF. And if you leave it to TIFF, it will download a GeoTIFF file. Now try to run it until here and let me know if it works. And finally, you'll be able to visualize the result.
Do we have to install rasterio? Because
okay, yes. So maybe there are some packages missing.
Yeah, the 2 packages are missing.
So I would suggest you to do pip install OpenEO, GeoPandas, raster.io, VioXarray maybe, and yeah, later we'll also use leaf map. So maybe before running the notebook, install those packages.
To me, it worked. Maybe it's just a matter of the kernel.
Of the kernel. Could be, because there are several different kernels. There's this geoscience kernel, this OpenEO kernel, and the base Python 3 kernel. So maybe check if you have used the OpenEO or geoscience. Anyway, I've noticed that if you select a kernel and you install the missing libraries, whenever your Jupyter instance is being stopped, you're going to lose these additional packages. So maybe just leave them in the notebook so that every time you can just redo that. So I guess that if you had this issue with raster.io, you were able to download the result, right? Okay, good. Someone had issues? No? Nice.
For some reasons, I cannot execute twice in a row. Just the first time, and I visualize the result. Then if I rerun again, no.
What's the error that you're getting?
I don't know. It can't import again rasterio for some reason.
Maybe you change the kernel in the meantime?
Maybe I need to restart.
Yeah, maybe restart the... Yeah. If you have issues, you can restart the kernel pressing this button here. And at the end, you can just, I mean, if you restart the kernel, for the visualization part, you can just run this cell and it should work. Remember that if you're using Python and you run asynchronous code like we did in this case, you'll have to wait to get the result, to get the file downloaded before continuing. So you're stuck. You have to wait for the result to come. And therefore, if you want to do something else in the meantime, in the same interactive Python environment, you have better to use a asynchronous call, so a batch job. Maybe it's already mentioned. I mean, here it's mentioned, but it's not mentioning that basically it stops. I mean, you have to wait for it. But yeah, we might also integrate that information. Just a logistic question, Milutin. For the afternoon, can we also continue working on OpenEO in case, or we should finish by 12:30?
I would suggest we first big data stories and then we continue.
No, okay, but I mean, if there's someone that would still work on it later,
yes.
Okay. Okay. Then let's try now a bit more complex example. It's provided in the again Python folder and landslide NDVI folder, and then open up the landslide NDVI notebook. So this sample notebook shows a simple way to detect landslides. It's a super simple example applied to an area where it's already known that a landslide happened. It's basically computing NDVI on different dates and then creating a difference, and via threshold method, it maps the areas that have been affected. Most of those examples would not be, let's say, scientifically relevant, but they just want to show how you can use OpenEO. Then you can basically build on top more sophisticated algorithms that might fit your research interests. But the examples are trying to be as generic as possible. So even the methods are pretty simple. There are also some more advanced stuff, but I would start with something simple first. So again, you can start importing the necessary libraries, connecting to the backend. The area of interest is on the Ischia Island in Italy, where in fall 2022, there were several landslides that happened after heavy rainfalls, which are unfortunately happening more and more frequently. Again, we use Sentinel-2 because we want to compute the NDVI index. And in this case, instead of manually computing the NDVI, specifying the formula, it's also possible to directly use the NDVI process, which automatically select the necessary bands to compute the index. Similarly to what we did using the wizard on the web editor. So you don't have to specify anything else. So this was the view of the situation previous to the landslide event. Now we do the same for another data cube after the event, and we download the results. Now I already have the result here. We open it up with raster.io, and we see the result appearing here. And this area, this elongated area here, is the actual main landslide that has been happening. And in fact, what we are doing is basically just the difference of the pre-event NDVI values and the post-event, and then we just get basically a threshold and visualize it here. So these notebooks shows you how to combine different data cubes. In fact, if we look at what we have generated, diff, you'll see that it's possible to combine different load collections. So load collection generates this virtual data cube, and it's possible to combine them. So ideally, we could have even different bands, different indexes being computed. And the process which is used to combine data cubes is called merge cubes. And you could also use it to combine data coming from different sensors. So Sentinel-2, Sentinel-1, Landsat, whatever. Let me know if it works for you and if you have any question about this. In the meantime, something that I didn't mention before. So the main website you should go if you want to have information about OpenEO is openeo.org. And here you'll find the links to all the documentation pages. For instance, you can get a general introduction of data cubes. You can get the getting started guide for how to install the packages. You can get the same getting started guide for Python, for instance, with some examples. And then here it's mentioned, for instance, for Python, the official documentation is not here, but it's in the GitHub repository as a GitHub page. And this is the main entry point for Python users the whole API documentation for the OpenEO Python client. Additionally, here, if you click on Services Hub, you get to another website, which is listing all the, let's say, registered OpenEO backends that are available. So you'll see here that there's the CDSC, which is listed as production ready with its URL. And you can also, again, inspect the metadata, collections, processes, and so on available on each backend. There's also, for instance, the one available at URAC with the collections and processes. And yeah, there's OpenEO Platform, Sentinel Hub, Vito, Mondialis, Google Earth Engine. The one mentioned here, Google Earth Engine, is basically a wrapper of Google Earth Engine with OpenEO, which was at the beginning developed by the University of Münster by Matthias Moll. And now it will be also updated and developed further thanks to another project. Yeah, and then if you would like to implement your own backend, there's also some documentation in terms of where to start. For instance, there's documentation about the Python-based processing engine based on Xarray and Dask, which is available here under Developers Xarray Dask Guide. And if you would like to try out to implement your own processing engine, you could also have a look. So let's go back to our Jupyter Hub. Did you manage to get the results of the landscape map? Other questions? Too easy. Okay, then let's move to a more difficult example. Now I would like you to clone another repository, which is the one of the online course that we developed. It's called Cubes and Clouds. Again, I'll post the link in Discord. So please, again, in the terminal window, git clone and the URL to the GitHub repository. And once you have the folder, Cubes and Clouds, please go to Lectures 3.1 Data Processing, Exercises, Data Processing. So I'll recap here. Lectures 3.1 Data Processing, Exercises, I think. 3.1 Exercises. Okay, and then let me know once you have this notebook open so that we can start. This is basically one of the final exercises of the online course. So it's already a bit advanced, but we already covered some basics. So I would like to show you a bit more complex example instead of focusing too much on the basics. Anyway, will be available in case you have some doubts. And it's quite interesting because the aim of this notebook is to show a combination of remote sensing data provided by the Sentinel mission with also in situ measurements provided by a local measurement station at the river catchment, at a river outlet measuring the discharge of the water. And what we want to do in this exercise is to map the snow coverage in the mountain and mapping and trying to see if there's a correlation between the snow coverage with the amount of water that comes out of the river downstream. You'll have to install some libraries as we did before. Scikit-learn probably is not necessary, but you'll definitely have to install RioXarray, GeoPandas, and LeafMap. You don't need to run this first cell. You can even delete it because it's necessary for the exercises when we are running this exercise within the Jupyter Hub environment provided for the online course to get the proper path. But in this case, we don't need that. So please install the missing libraries. And once you have them, we try to import them. If you're still missing something, then install it. Yes, okay, yeah. Because every time that you restart the workspace, you have to install them. Yeah, that could be also a feedback that we can provide to the CDSC maintainers. So trying to add some use pretty common libraries like GeoPandas, which is not by default available. Let's see. It takes some time. Okay, it installed the libraries and imported them. Then again, we connect to the OpenEO backend, we authenticate, easy. We can also, there's this method which is describe account. We can get the information of our account if necessary. And then we start looking at some vector data. We have a GeoJSON defining the region of interest. It's in Valpasilia in South Tyrol, and it's the catchment of this river. So we load the GeoJSON using GeoPandas, and then we visualize it using LeafMap. Let's see if it appears. Yes. So it's basically this area. So I'll zoom out so you see where we are. It's in the province of South Tyrol. Euroc is based here in Bolzano, and you also might know Milan, which is a pretty famous city. So it's basically this whole catchment area of the Adige River. And we'll specifically work with data only in this particular area. So now again, we list the collections that are available on the backend. Again, we yet again use Sentinel-2. I'm sorry, I haven't prepared examples for other sensors, but you'll find some in the community examples. So this is again the metadata. We have already seen it. And now we have to define our workflow. So what we are going to do. So we load the data cube with the defined parameters. So the area of interest given by this vector data. So this GeoJSON. We compute the NDSI, the normalized difference snow index. This index will let us understand if there's snow or not snow on the map with a threshold. Then we'll also apply another quite common step, so creating a cloud mask and applying it to the data to remove the clouds. We'll visualize one date of the snow map to see how it looks like for a single date. And then later we'll calculate the catchment statistics for the whole time series to get a single value time series of snow cover and cloud cover over the catchment area. And finally, we'll be able to filter the time series by the cloud percentage on the catchment and basically remove the noise from the time series. So now we just get the bounding box from the geodata frame, which has been created from the GeoJSON file. We then introduce another step in the load collection. So it's also possible to filter out acquisitions given some properties. For instance, the cloud cover. We would like to, in this case, just get images that have a cloud cover less than equal 90%, which is still pretty high, but we'll filter out the clouds later on. But for some cases, it's really important to immediately filter out the cloudy scenes so that you spare time because it's not processing useless data. And you also spare money/credits because the backend is not processing this data and therefore it's reducing the amount of resources which are being used. So a suggestion, always start conservative with this number, so less than 50% or 40 cloud coverage, and then in case, depending on your application, you can include more images. So now we just defined our parameters. We're interested in the spring period of 2018. We start creating the data cube with the Sentinel-2 data, and then we compute the NDSI. So again, pretty easy. We create two objects, one for the green band, one for the SWIR band. We write down the formula, and we have the NDSI inside this reduced dimension here. Now that we have this NDSI value, we want to create an NDSI map. So we basically just use a threshold. We say for all the pixels that are greater than 0.4, now we'll create a Boolean mask. So all the pixels that are greater than 0.4 will become 1, and the ones that are less than equal 0.4 will become 0. And this will be our snow map, defining the pixels that we consider to be snow covered and the pixels that should not be snow covered. Additionally, as I was saying, a super crucial step for every analysis with optical data is cloud masking. We don't want the clouds to interfere with our analysis. So we use the scene classification layer provided by level 2A of the Sentinel-2 processing. You can get an overview of the meaning of the various labels at this link. Somewhere. Anyway, the thing is that there are different values that correspond to different classifications of the data below. So there would be water, snow, ice, bare soil. We are interested just in the cloud ones. So we'll filter out cloud medium probability, cloud high probability, and cloud shadow, and combine them in a single Boolean mask. So this is a Boolean operation. So we are basically creating 3 Boolean masks and then combine them. So if the data is 8 or 9 or 3, and then we get our cloud mask. Now that we have the cloud mask, we want to apply to the input data cube. The process is called easily understandable mask. This is the input data cube that we just created. And we can also use a replacement value. And in this case, we use the number 2 so that the result will be 0, which means no snow, 1, which means snow, and 2, cloud. And this is the representation. So on one branch, we compute the NDSI. On the other branch, we compute the cloud mask, and then we combine them. Next, we start also combining the vector data that we have as input. There's this process called mask polygon, which takes as input the raster data cube and masks out all the pixels that are outside the vector cube that we give as input. We can pass it directly as I think this is a shapely polygon. We can pass it directly like this. And again, this data cube will contain the whole workflow with the final step, which is the one that we just did, masking out and keeping just the data inside our polygon of interest. Now we can visualize one time step. I wouldn't suggest you to try to download it because it might take some time. The NetCDF should be already available. And again, as I told you, if you execute this cell, then you'll have to wait until you get the result to proceed. So later you can also try to download it, but if the NetCDF is already there, we can already have a look at the result. So this is the map that we get for February 11th. So we have the areas at 2 that should be clouds, then 1 snow and 0 no snow. This area here is due to the fact that basically the area below corresponds to one Sentinel-2 tile and the one above to another. So basically, this area for this date in this part there's no data, and that's why it's set to 0. Then we want to compute the statistics over these snow, no snow, and cloud maps. We're going to get the number of pixels in the catchment, so the total number of pixels available, the cloudy pixels and the snow pixels. With these numbers, we can then compute the snow covered area in terms of percentage corresponding to the area of interest. And then we'll filter out the cloudy time steps. So if there are too many clouds covering our polygon, we are not going to consider that in the analysis. This whole step, it's a bit maybe difficult to understand because what we are doing, we firstly threshold the map, we create a dimension, we compute the statistics, and finally aggregate everything into one data cube. The most important step is this aggregate spatial call. Aggregate spatial is a pretty important OpenEO process that defines how to compute statistics over vector geometries. So the geometries in this case is just a single one, the one that we have seen before. And the reducer that we use is the sum, because now we created several 0-1 Boolean masks. So one for the cloudy pixels, one for the total pixels, and one for the snow pixels. And the sum will give us exactly the number of pixels in a single integer value, which later we can use for showing the time series and performing our analysis. Here you can start your batch job and wait for the result to come. This is another way to run jobs. In this case, start and wait, it's basically doing the same as a synchronous call, but creating a job. So it creates a job, starts it, and wait for the result to come. It might take a lot of time to run, so maybe have a look at the results that I have here, and later also try it out. Once that we have the result, in this case, we're not downloading a raster file, but we did download a time series in JSON format. So we can read the time series. We can have a look at some samples in the data. We can reformat the data as a pandas data frame, which is then easier to analyze. We can have a look at the number of pixels that are available. And then we start computing some statistics. So we can divide the number of cloudy pixels to the total number of pixels so that we get the cloud percentage, the cloud coverage for each time step. Here you see the value. So for instance, the 3rd of February had a cloud coverage of 91%, and we'll discard it because it's too cloudy. And finally, we can plot this cloud percentage. You'll see that there are some days where this cloud coverage is well above this threshold limit that we set 25%. And if you look at the data in this way, you're not seeing anything meaningful, probably. Then we start computing a snow percentage in the same way. This, it's a bit more understandable. So at the start of the season, the melting season, we see that the snow covered area is higher, and then it starts decreasing, but there's still a lot of noise in this time series. Finally, if we want to filter out the cloudy dates, we just use pandas to filter out data which has a cloud coverage greater than 25%. And then we finally plot the result. You'll see that the snow covered area for the catchment is pretty high in winter, and when we get to spring and summer, the snow cover area decreases a lot until we reach the almost zero. And we could also store our final result to a CSV format. Now you have seen a full workflow interacting with the cloud. As I was saying before, it's also possible to prototype locally. And now I'll introduce another way to use OpenEO. It's called client-side processing, which means instead of interacting with the backend, we'll just use data which is publicly available via stack catalogs, and basically redo the same workflow, but locally on your Jupyter instance. It could be also your local computer. Yes. Well, I mean, you could just see it updating. If it's something that you know it takes a little amount of time and you don't want to have several times to get the status, you can directly run that, wait until it finishes, and yeah. Yeah, because the job is still running, so you could still get the information later on. But just one detail, let me show you. So if you close the notebook, you'll still be able to access all the jobs that you have run. And to do that, you would have to do connection list jobs. And you get the list of all the jobs that you have created. And if you want to retrieve the information of a particular job that you run, this was the last one that I ran, you would have to do job equal connection dot job. You provide the job ID. And then this job object contains all the information about the job. So this was actually the example that I created before with you. And this shows the nice interactivity between the different clients of OpenEO. So you can create a job with Python and see it on the web editor, or the other way around. And you can get all the information, the process graph. And to get the results, you would have to do job.getResults. Those are all information that are covered in the various sample notebooks that you can find in the repository and also in the documentation. And doing the job.getResult, you would get the stack metadata as seen on the web editor with the links to the TIFF file and the whole metadata set. But as I was saying, sometimes you would like to prototype with OpenEO without having to use credits, so without incurring in costs. And something that we recently developed is called client-side processing, and the documentation is available. It's just for Python for the time being. It's available under the OpenEO Python client documentation. I'll send you the link on Discord if I manage to select that tab. And it will basically allow you to create OpenEO process graphs and compute the result locally. The nice thing is that then once you're sure of what you're doing with OpenEO, you can then use the same process graph in the cloud and basically scale up your algorithm. So the example using the client-side processing functionality it's in the same folder under alternatives. And here, by the way, if someone wants to do it in R, there's also the R Markdown file with the same workflow. But now I would like you to open the data processing stack notebook. Again, you'll have to install probably just one missing library, because if you install RioXarray, GeoPandaset, and LeafMap, you don't have to run this, but you'll probably have to run pip install OpenEO local processing, which is also installing the necessary libraries to run OpenEO process graphs locally. Again, we start with importing the libraries. Now the main entry point. Oh, okay, I have to install it again. This notebook, it's under, again, in the Cubes and Clouds exercises, lectures, 3.1 data processing exercises, alternatives, and data processing stack. And it's the same one that we used at Big Data from Space last year with Lorenzo. So now I'm installing the missing libraries to process the OpenEO process graph locally. In the meantime, I'll show you where the Python implementation of the OpenEO processes lives. The GitHub repository, it's called OpenEO processes task, because the implementation is based on Xarray and Dask. And basically, all the processes that are available are in here. For instance, we have seen the aggregate, we did use the aggregate spatial, and here under aggregate, you can actually see how the process is implemented. So again, the whole code is open source. You can directly inspect how the algorithms are implemented. And in case you don't like it, you could modify it, open a pull request, and contribute to the project. So let's go back here. Now the libraries should be installed. Let's execute it. And the workflow and exercise is exactly the same as the one that we did before, interacting with the OpenEO backend. But now we're not interacting with any OpenEO backend, but we'll just use data provided by publicly available stack catalog. So again, we are showing the area of interest. Now we'll use Sentinel-2 L3 data collection from Microsoft Planetary Computer. As I was saying, Milutin, it's also possible to do that. So if something is missing from the data collections available, it's also possible to try out and use publicly available data from other providers. So again, we get the bounding box. And similarly, in this case, since we're using data coming from a stack catalog, the first process is no more called load collection, but it's load stack. Additionally to the various parameters, I also set a cloud cover property and a specific Sentinel-2 tile that I want to process, because I already know that most of the area that we're interested in, it's covered by the 32 TPS UTM tile. I start creating 2 data cubes containing different bands. These are, let's say, kind of advanced way, because you see I'm creating 2 different data cubes, one for the band 11 and sync classification layer, and one for the band 3, because I do already know that the first 2 have 20-meter resolution, and the green band has 10-meter resolution. But if I would try to load all of them together, the 20 meters would be resampled to the 20 to 10 to align all of them, and therefore I would just waste some computational resources for nothing. So I load them separately, and then later we'll align them to a single resolution, which will be 20 meters. Here there's some commented code. Using the client-side processing functionality, as I said, you could also use data which you already have. So you could download the netcdf containing the whole data cube that we are interested in, and then later on processing it offline. In this case, we just proceed, but that would be also possible. You would just have to uncomment the code, download the netcdf, and then reload it this way. As I was saying, now we want to align the 10-meter bands and the 20-meter bands. We use this process called resample cube spatial, which basically is taking as input an input data cube, which is the green band, and then a target data cube, which defines the resolution and the projection. Now, in this case, the data cubes are already aligned. They have the same projection, but they have a different resolution. And therefore, it will resample the 10-meter data to 20 meters. And next, we are merging them together. So basically, we'll get a data cube with 3 bands, all of them at 20 meters. Again, we are computing the NDSI. And we can have a look at the process graph. Again, we compute the the snow map with a threshold. The snow map is computed by setting the threshold in a reduced dimension process. So basically, another thing that you might see is that at this step, we create this snow map. No, previously we created a snow map, NDSI here, and it's in reduced dimension. But then later on, we set another step, additional step on the NDSI. And it's not adding a new reduced dimension process, but the Python client is smart enough to pipe and add this process directly inside the previous one. So the Python client also helps you to build an efficient process graph without too much worries. Okay, and yes, oh wait, I deleted the. Okay. Then again, we create the cloud mask. Here we have the correspondence between the labels and the values. Again, we get all the cloud related labels for the scene classification layers. We apply the cloud mask to the snow map. And then we can visualize one time step. Previously, when interacting with the OpenEO backend, we were creating the OpenEO process graph. And then when we were either downloading the result or creating a job, it was sent to the backend and processed. In this case, we are creating again the process graph locally. And then when we call .execute, it will execute the process graph locally, and it will return an X-array object, which can be further used for experimenting. So now it's basically downloading the data from the public stack catalog. No, not yet. Sorry, because when we are getting this X-array object, it will build still a view of the data. So a dust-based X-array object, and therefore now it's just building. Given all the operations that we have created, it will just create a view of the final data cube that we are generating. And then later on, if, for instance, we will plot the data or inspect the single values, that part will actually trigger the download of the various images that we selected from Stack. Those concepts, I guess that you'll see more tomorrow in the Pangeo tutorial. In the meantime, are there questions? Did you manage to install the missing libraries and run them? Yes. We are almost to the end. Oh, error. Could not find. Okay. Yes. So as I was saying, Dask is being used to process data in a parallel manner and to manage lazy loading of data. So we also need to do pip install Dask. No, it's a type. Yes. Okay, let's see. Now I have to rerun it. By the way, let's have a look at this object that we got before trying to plot it. You see that this is an X-array data array containing one band, one time step, and Y and X dimension. This Y and X dimension correspond to the area of interest that we selected. One single band, it's the generated classified snow map, and one time step because we selected a single time step using the OpenEO process filter temporal. And now let's plot it. So this will trigger. No. Now probably I have to restart the kernel. Okay. Yeah, but I did install it now. Maybe I also have to install distributed. It was already installed. Okay, then let's just restart the kernel and do it from scratch. No, it shouldn't be necessary to import it. The kernel crashed. Yeah, that's something that I've noticed from the Copernicus, this Jupyter environment offered by CDSC. Sometimes if you install third-party libraries, it might crash. Let's see if I manage to run it. Otherwise, I'll try a different kernel.
Exactly before.
Yeah. Yeah, in case we can also continue later. It's not an issue. But basically, I'll show you the final output because it should be already here. What you'll get is, again, a time series of values. And finally, also the actual values. And finally, the unfiltered time series, the filtered time series, and finally, more or less the same result we got before. You can also compare it here. Could be slightly different because the data is being provided by two different providers. It might be processed slightly differently. And also the process implementation there might be some difference in terms of the floating point rounding. And finally, this step was missing from the previous notebook because it's in another step, but this is all together. You can also directly see the relation between the snow-covered area and the discharge rate at the river outlet. So you see the more snow it's melting, the more water we get in the river. Yeah. Okay. I think that we can stop here. You can also try it out later in case. And if the kernel crashes, either you do it on your computer with your Jupyter environment, or maybe try to select another kernel and reinstall the missing libraries. That might do the trick. Previously, I tried it and it was working, so it's an issue of the server. Questions before lunch? Otherwise, you have time to reflect on it, and later we'll have time in case. Other questions from the online audience? What do you think about this functionality? Could it be interesting for prototyping and getting into OpenEO? Then I think that we can close for now. Thanks for listening. By the way, I will upload the presentation on Discord. In the presentation itself, I also prepared a list of frequently asked questions about OpenEO. I didn't mention machine learning, for instance. I didn't mention the use of defined functions, which is another way to combine custom code and run it in the cloud. There are quite several things that could be mentioned and tried, but we would need a full day. And here I included some interesting points that might be meaningful. Yeah. Yes.
Just a question, and the available kernel are documented somewhere?
The thing is that I'm not part of the CDSC team, so I'm just using it. So I don't know.
Discover just it just discover.
You can just try out and see what's missing.
Okay.
But there's the CDC forum. So in case you have any question, you can just refer to that and post a question.
Okay.
Maybe it's documented somewhere. Probably it's also on GitHub because there's a specific repository for everything on GitHub, also for the Copernicus data space. So probably there's also an environment specifying the libraries there. Good.
Okay, good. So let's then make a break for lunch, and yeah, we start in 1 hour with big data stories. So 2 big data stories, and then we continue with OpenEO.
Yep.